Potential energy. Potential energy we can define as the energy stored in a body due to the position of the object or due to the change of its shape or size of the object, right? So we know that if you use the elastic material, so if you change its shape and if you release the load applied on it, so you can say that it will regain to its original shape or original size. So that means having some energy stored in there during their deformation. So if you deform the object, so its shape or size can change. So due to that case, there's some energy stored there. That also we consider as a potential energy. So if you want to place any body in the force field, we need to do some work against the field, right? Because the field always given a force on it. So you need to do some work against the force applied by the field. So then that energy, that work done is stored as the energy of the body. That is also considered as a potential energy. So then potential energy we can define like that's energy stored in a body due to the position. Position means which field which it belongs or to shape the change of its body, right? So then that energy considered to that case we considered as the potential. First you write under the potential energy. Right there, the energy stored in a body, energy stored in a body stored in a body due to the position, due to its position. Sorry, we written the so we wrote up to 2000. So then the two forms we will discuss, that the gravitational and the one, right? Sorry for that. There are then two types, the two forms of the potential energy. There is a gravitational potential energy and elastic potential energy. We will discuss this one. Then first write the topic is the gravitational potential energy. Right? Normally we call it GP. Right, the gravitational potential energy. Okay, then write the gravitational potential energy, that is the energy stored in a body due to the gravitational field. Okay, then write there the gravitational potential energy. The gravitational potential energy is the mechanical energy stored in a body. Mechanical energy stored in a body gravitational energy is mechanical energy stored in the body due to its position in the gravitational field. Then right, separate right, yeah. All the bodies all the bodies on the earth, and around the earth are under the gravitational field. Therefore, therefore, it needs to do work. Therefore, it needs to do work to bring an object. Needs to do work. To bring an object away from the Earth's surface. Away from the Earth's surface. Away from the Earth's surface. Against the gravitational attraction. Against the gravitational attraction. Then the energy of the body will be increased. The energy of the body will be increased. This energy is stored in the body. This energy is stored in the body, and it is called gravitational potential energy. And it is called the gravitational potential energy with respect to the initial level. With respect to the initial level. Which is important, that is the initial level, because to measure the potential energy, we need to select an arbitrary level. So we can consider that level has the potential energy is 0. And with respect to that level, the above which the potential energy we consider as positive. And below that level, we consider the potential energy as negative. Consider here when you measure this, all the heights and everything, you need to measure from the center of gravity, right? Not from the surface actually. So we consider this level has the potential energy 0 level. The PE means potential energy. So potential energy is 0 level. So we call it the reference level, right? We'll write in that, it's better. That's potential energy is 0. And weight is downward. Let's say it's raise the height h. So we need to do work against the weight of the body. Right. So you need to apply to bring this body this point. You, let's say you need to apply the force F there. And also if you want to bring it down, the same thing you need to do. Right. To bring it down also you need to apply the force on it and to bring down. First you can draw this. First you can draw this. I will write there. It's two cases I'm considering. Take it down and take it up. You can write that's a minimum force minimum force required to raise the object. Raise the mass simple m. This is simple. It is F equals this mg. It's in taking up. Then you can write as work done. Work done when m raised to height h. Let's write that is F into displacement. So that's F minimum force is mg into s. S means here h, right? So the work done is equals to the mgh. So this is stored as a potential range. Should write, yeah. Okay. If the same mass when you bring this down, here you need to draw this not from here. It is should be drawing from center of gravity to center of gravity, right? That's a height. This h means there is it is a distance travel from its center of gravity to center of gravity. Center of gravity. You need to get the height to the center of gravity of the considered reference level. And here same way you can write this work done when m lower to height h. Sub you can write as also fs, the downward force unit of time. To bring it down in the same way, the same force you need to apply. And up to this point, that force is there. Tatharyatmika mg weight taking in of accelerated. So then that force is opposes to the weight is down. So then you can write minus mg. Okay. It will be minus because that reference level has the range is 0. Downward it's negative. It's okay. Finish. You know. If you finish right, let me know. Yeah, actually, this lower to height means it's actually lower to a depth. Right, actually, it's depth. It's more suitable where it's depth. Hi. Okay, actually, that's then this work done, we can consider as a story in potential in the body. So then right there, this work done is stored as a potential gravitational potential energy, right? This work done is stored as a gravitational potential energy, the body. So then the gravitational potential energy of any body, you can write it is mgh. This is the potential energy with respect to a reference level, right? So at the point h from the reference point, right? And also you need to know this equation you can apply only when this h is much smaller by comparing with the radius of the earth. You can write this as a note. We will discuss this more further in unit 5. So but in here you mention it not that h is not that you can write as this equation, the above equation and the above equation is valid only if h is more smaller than r. R means r is the radius of earth. Radius of earth. That is 6,400 kilometers. You know that's when you have heard about this, that g is not a constant above the earth's surface. When you raise the body, the acceleration of gravity will be reduced with the altitude. Right. So that's the reason. If then the mgh is not a constant one. So it's not only depend on h, it's also depending g. So j will change with the height. So then we can write this equation only when we can consider if h is much smaller than r, so then the g is remain constant. So actual equation is gb is equals to the, that is mgh divided by 1 plus hor. This is a real equation. 1 plus hor. So as h much smaller than r, so hor is much smaller than 1. So that's 1 plus hor is approximately equals to 1. So then the purification potential energy is equals to mgh. This is equation come, that's mgh will come from this equation. So it's so in the in this assumption is made. Right. You write it as a note because in the under the lesson, the unit 5, that's gravitational field lesson, we will discuss this in more details. But in gravitational, but in the mechanics, we can use this MGH because in mechanical system we discuss the heights about 1 kilometer below, right? So that means 1 kilometer. We're comparing with this how 6,400 kilometers. The 1 kilometer below the height are negligible. So then you can use the MGH. Okay. And also this potential energy is not the absolute value, right? So we cannot say it's any it's zero. It's zero at infinity. But you can select the arbitrary reference point or reference level. So then you can consider that level has zero. So we always give the potential energy with respect to the initial level of reference. The reference level we consider as a potential energy zero. Okay, you can try and write that one also there. The gravitational potential energy is always measured. The gravitational potential energy is always measured with respect to a initial reference level. With respect to a initial reference level. Initial reference level. It's considered the potential energy at that level is zero. Potential energy is that level is zero. That level is zero. And then all the potential energy is measured with respect to this level. And all the potential energy is measured with respect to this level. Okay. Then write the elastic potential. Elastic potential energy. Right under that, the energy stored in a body. The energy is stored in a body due to the change of its shape or size. Energy stored in a body. Energy stored in a body due to change of its length or size. Sorry, the shape or size, right? Shape or size. Right. Okay, then write now that's energy stored in a spring, and the energy stored in a stretched or compressed spring. Let it start in a straight, stretched or compressed spring is considered as, can be considered as elastic potential energy, can be considered as the elastic potential energy. And due to this energy stored in a spring, due to this energy stored in a spring, the spring can do work. The spring can do a work. Then අපි spring when you place the body on a spring and press it and compress it and then release, so it will moving with some velocity. That's spring can do work because of this energy stored there due to shape change or size change. Okay, then we consider that's the work done by a spring. This right, consider a block shown in the figure extend the spring extends the spring by the distance by a distance simple x. Like this simple mass is m, and then the force thing on this spring, it's considered as F. Okay, and then write the spring constant or force constant. You can write the let the spring constant, let the spring constant or a force constant of the spring be simple k. This force constant or spring constant of the spring be simple k. Okay. Then write that force exerts on the body by the spring. By the spring, that is, you can write as equals to F. So this F you can write the mechanics we discuss. This F we can write it is proportional to this X, and we write as minus Kx. This minus sign is put here because of it's always opposite to the F is opposite to this displacement X. That's why this negative sign we put there. Here the magnitude on the force we considered, right? But in this case, that F is proportional to X means when there is no any extension, that X equals 0, that's the force applied on the spring is also 0. The body has no force on it. And in this position, let's say has a force, you can write that is equals to Kx, the magnitude of this force. But a negative indicates opposite direction. Okay, then the average was exerted on the body. That's subtracting its average, that's equals to the initial force is F initial plus F final force divided by 2. Initial force means when the X equals 0, so that is 0. Final force means it's the force that is section is X. Its extension is X, so then it is F divided by 2. So that's equals to therefore 2 here. That is F of 2, right? This F average force is this one. This is because you can see here that when you apply the force, right, in the extension you draw the graph, you can get this kind of graph actually. Force is 0 at X equals 0, then so energy is equals to this area, the work done. You can write due to this area. So here also you can write like this. Therefore, then work done by the spring is equals to the work done by average force. So we can write W average force multiplied by the displacement. That's force multiplied by the displacement. So average force is half the force applied, and X F equals Kx you can write, then you can write this W equals half Kx. You can write this average work done or mean work done. mean work done, I guess half kx gamma. So come right, half kx gamma. So area of this gas is also equal to half fx. So f is k, x, then you can write. Right up to this point, and let me know that you can keep it in mind that when the spring is there, so it's the work done or energy stored in the spring, always you can write as half k square. That's if the spring is not compressed or stretched, so no work done. So it's energy, there are no any energy stored in here. So there should be the extension or compression and the spring to do work. If it is writing, let me know. All right. You are not cleared some points, so you can let me know. I can explain it again. This is the force applied. With this part we discuss that is force applied by the springs. Also, that is it, because kx, the negative sign you don't need to consider because it indicates a direction. If in the case of here the force applied by the spring or on the spring, you can consider it as a positive or negative way, right? So you can get to that because you need to get the energy stored in the system. So then you can consider that's positive always. So that is the work done by a spring when it is stretched or is compressed at distance x. Should finish the writing. Finished it. Okay, then next page, I'm going to the next page and then right there. Position right then this energy, this work done, sorry. This work done is stored in the spring. This work done is stored in the string as elastic potential energy. So therefore, elastic potential energy of a spring you can write like the half kx. Keep it in mind. Any spring, or in the case of is we consider as a rubber band, this k we use as a force constant then, right? So both the same way, that's k is a spring constant or rubber constant or force constant. Force constant. So its meaning is that force required to apply on the spring to stretch it by 1 meter. Extension curve run. Okay, you can write the question. Example, right? Then example there. What is the potential energy? What is the potential energy? Potential energy of the block shown in the figure below. Of the uniform block, right? Uniform block shown in the figure below. Mass is capital M. There are two figures A, B. You can find what is the potential energy of these two figures. So this level consider the potential energy 0 level. Okay, right. It's the same body, but in two different orientations. Right. In this case, we need to measure the height to the center of gravity. Okay. If you forget about it, then you can write there. In the case of your measuring or writing the potential energy, you need to height to the center of gravity of the body from the reference level. So in this body, center of gravity is at the intersection point of two symmetrical lines, somewhere here, and where the weight of the body will act. So height to that point is A over 2, the half of the side. So then the potential energy of this place, that is mg A over 2. Right. And here also similar, but its center of gravity is above the previous. So the potential energy of the body, and here it is mg p over 2. Okay, that's in this case. First case, potential energy is smaller than the second case, B case, right? So that means that that the object is more stable in this position than this. This position A is more stable than position B, because in this position their potential energy is smaller. Then it's a higher the potential energy of a system or body, it is more unstable. If you want to be stable, you need to reduce this potential energy. That's why when you are standing up, so you have much more energy, more potential energy, you're high, and it is not much stable. You are be you can be stable then if you sleep. That's why sleeping is more stable, because more stable and also more convenient for you. Rather, you are standing. Stable ගතියක් තියෙනවා. No energy, that's the minimum energy state you have. Okay. Write a second question. Second question, right? When a block of mass 5 kilogram, when a block of mass 5 kilogram is attached to the free end of the vertically hung suspended spring. Attached to the free end of the vertically suspended spring. It is stretched by 4 centimeters. It is stretched by 4 centimeters. Find the elastic potential energy stored in the spring. The elastic potential energy stored in the spring. Stored in a spring when 8 kilogram load is attached to it. The suspended, right? When the 8 kilogram block is attached to it. Okay, you try to do it. Okay, let's see here then. If you hung 5 kilogram, right? So its extent by 4 centimeters is given. That the force on the spring you can write it's kx. Force means this 5 kilogram you had, that's a 50 Newton. And k you need to find. Then x is 4 centimeters, 4 into 10 to the minus 2 meter. Then you can find the k spring constant. So it is equals to the 5000 divided by 4, that is 1250 newtons per meter. Spring constant. And when you hang 8 kilogram, now and there is this part now, right? So now when you hang the 8 kilogram, so this will stretch more. Then the stretching, let's say it is x. You can find it now. You know that if equals kx and then x, you can write the force is 80 Newton now applied, and k is 1250. Yeah, already calculated, right? So that is in meter. Then you can find this value. Let's see, you can simplify. Place it here. Yeah, it should be that's 6.4 centimeters. Right. So then the elastic potential energy stored there, in this case, the half kx square or half fx. Half k is 1250 and x is 0.064. Because of centimeter, that is 0.064 meter. That's square of this. So it is 2.56 joules. That's how this elastic potential energy calculated on a spring. Is it clear up to this point? All right. I think it's clear for all. I got the next point that we will discuss the conservation of energy. Then hide the conservation of energy, right? Right, the principle of conservation of energy. Principle of conservation of energy. All right, let's see then what is the energy conservation. According to this energy conservation, that's in an isolated system or isolated system means there is energy uh, of the system is not goes to the outside, or then also the external energy will not come to the inside, right? That means energy will not out of the system and energy will not come to the system. So in that isolated system, we can say that the total energy is constant. So it's the energy cannot be destroyed or it cannot be created. So it remains constant. The energy can only transfer from one form to another form. That the potential energy when can conform, that's converts to the kinetic energy. Or potential energy can convert to the other forms of energy like the heat, sound, light, like this. That's the only thing you can do. Energy cannot be destroyed or energy cannot be created. If the energy cannot be created, how can it produce the energy in the power plants? We call that the energy production. Is there any production of the new energy? No. Actually, that's convert one form of energy to another. We consider about the power station and the hydropower station, how they produce electricity. They store the hydro, that's water, in a tank. The tank is much above, the power plant is below. So due to that height, the potential energy difference is there. So the potential energy of water then converts to the kinetic energy of the turbine. Then turbine is directly connected to the electric generator. So then it converts the kinetic energy to the electrical energy. So that's the way we do it. We are not producing new energy. We always converts one form to another form. Right, in all the kind of power station they do like the different forms they are converting. Then in a thermal power station, the thermal energy they convert to the mechanical energy and then it converts to electricity. So different modes of or different forms of energy we use in the different power station, but we are not producing new one, right? That's in. And also in some cases we call there's some loss of energy. So if the energy cannot be destroyed, so there's no any loss of energy. But if you consider about the mechanical system, right? Think about, we are considering about mechanical system. In a mechanical system, there are mechanical energy, that's a required energy to get at the output. That's mechanical. Let's say if you want to give some push on the body, then you need to make it in motion. That's a kinetic, and you need to convert the energy given to that body to kinetic. But when the body is moving, due to the friction, it gets some heat or it gets some hot, right? because of that two surfaces are in contact. So then some heat is produced. So, but that heat is not not the energy required in that mechanical system. So that is unwanted energy. So the unwanted energy in a system we can consider as the loss of the energy to the system. It not really means the loss of energy. It means that there is the energy unwanted to that system. If you use the light, you are given electricity to it to light light it up, right? So, but we know that when you given the heat, light, electricity, other than it gives the light, it gets heated. So heat is unwanted energy of that system. So we can consider that heat as a loss to that system. So that's the way we consider about the loss. That means not the destroying of energy. It's another form of energy. The loss of energy means it's another form of energy. So in any system, then you have to consider like this. So according to this principle of conservation, there are two conservation laws in your syllabus. One is already discussed, that is the quantum conservation, right? So second one is this is energy conservation. If let's say in the questions you don't have have nothing, I think sorry, you don't know how to do the question in any mechanical question you have given. So but you don't know how to do it, at least try to use the momentum conservation and energy conservation, because that's always can horse you can do it, because most of the cases in the system you need to identify how that energy conversion is there, how that momentum conservation is there. Based on these two principles, actually normally that's in higher mechanical system questions you can solve. So if you don't know how to do it, or if you don't have get anything to do, try to apply these two conservation laws always, so that it is more helpful you to solve the question. Okay, first we write the principle of conservation of energy, and then in mechanical system we reduce this conservation of principle to mechanical energy conservation, because in a mechanical system we have to consider the mechanical energies. Okay, first you write the energy conservation principle of energy conservation right there. Then write first write the principle. Right, the energy cannot be created or cannot be destroyed. Energy cannot be created or destroyed. In an isolated system. An isolated system. Sorry, here the energy cannot be created or destroyed. In comma, you're gonna use destroyed and in an isolated system, that comma, energy cannot be created or destroyed, and in an isolated system, total energy is a constant. It's constant or remain unchanged. Constant or remain unchanged. then write ekata maliyanda, and energy can only be converted or transferred, converted from one form to another form. One form of energy to another form of energy. To another. That's enough. Energy can only be converted from one form of energy to another. To the other. Right. So that's the thing only. After that, you can write this term. You need to know that this term, what is the isolated system. Okay, right. Then write there. Isolated system is an isolated system. Right? And isolated system is an isolated system is a system is a system which cannot transfer, which cannot transfer any form of energy, cannot transfer any form of energy from the system to the surrounding, or to the from the system to the surrounding, or from the system to the outside, the outside, or from outside to the system. That means just like a closed system, right? So if you have a body like this, so this system, no energy transfer from this system to the outside, but no energy come into this system from the outside. So in that kind of system, we can consider isolated system. If we consider this universe, the whole universe is also, it's a best example for the isolated system. This example, you can say like that. So you need to know here. In energy conservation, you can consider all the energies, right? That's all the energy forms, any form. Let's say lights, sound, heat, and mechanical energies, kinetic and potential, like that. Any form. Then you need to know this principle. And then I will write that the side, write conservative forces and non-conservative forces. Conservative and non-conservative forces. Conservative and non-conservative forces. This means that conservative forces mean if that work done by a force does not depend, that we can consider as a force done by a force does not depend on the path of the objects is taken. So we can call it a conservative force. It does not depend on the path of the body is taken. Right? If it depends on the path, you can consider unconservative. As example, the gravitational force, that's in the gravitational potential energy from this point to this point, you bring the body, let's say this body is there, and you can bring this body in different paths. We'll discuss this. You can bring it directly this path, and another can take this body to this path. Another one can take this body to this point, and from here to here, it's a different path like this. Different paths you can follow. Bring the body from this point to that's the same. That's the difference between these two levels. Let's see H. And this is the potential energy 0 level. Let's see mass of the bodies. This is path 1, this is second path, and this is third. In these three paths, the potential energy increased or potentially stored in this body at this point position P A here. So you can write this as mgh in all paths. In this path or this path or this path, you bring the body, it's same. mgh is same. It's here the work done by the weight of the body there, right? So this weight is then considered as the conservative force because it's all the parts the same work done or same work done, right? So no change in work done due to the path of it being taken. So that's forces are called conservative forces. Here it's a practical example. You get some cases we use staircases in this format to climbing up, and in some is it the same height, we can use the staircases like have you seen this kind of staircases or use like the staircases, they've been like this. In this both the cases, the same work done. Same work done. Work done is not different. It's same. So it's not depend on the path. This work done by the weight is not depend on the path of the bodies taken. So it's called the conservative forces. In the case of non-conservative force, it depends on the path. As example, if there's a friction, the work done by the friction, it is depends on the path, because the path is different paths they have in the different frictional force applied there. Then the work done against the friction is also different, right? So it is not a conservative then, it's non-conservative force. But a conservative forces, that's a gravitational force, is a conservative. Okay. We can say this is in the other way. If your body is there, you bring this body to this point, that's A to B, and in a cross path, you can bring the body back to the A. If the total work done is then 0, no work done. It's not dependent on the path, but then 0 work done. If you raise it up, so it's where potential energy increases mgh. If you raise it down, so it's lowered down, so its potential energy is then minus mg. With respect to the above level, it's minus mg. So then total, you can consider it as 0. So if in a cross path you bring the body, if by force applied on it. So if the total work done is 0, we can consider it as also the conservative force. Conservative first you write under this conservative and unconservative forces. Right? A force is conservative. A force is conservative if the work it does, if the work it does on a particle, the work it does on a particle that moves through a closed path, is 0. Is 0. Is 0. Also, the work done by a conservative force, on a particle, conservative force on a particle is independent of the path, the particle follows between 2 points. Paths that particle follows between 2 points. Okay, then right, that is the work done on the particle between 2 points. The work done on the particle between 2 points is the same for all paths, is the same for all the paths, connecting those points. Write examples. You can draw these diagrams, and after writing this example, write examples for this conservative forces. The gravitational force, this is within bracket, write the weight, and electrostatic force, magnetic force, you write this, those are examples. So you can write then draw this diagram and you can get an idea. This work done during this 1, 2, 3 all parts are if I will write as work done by the path 1 and work done by the path 2, by means it's work done along the path 2 and along the path 3. So all the cases is MGH. So this work is done by mg, that's mg is a conservative force. WI1 means W in this first part, second part, like this. Okay, you copy down. හරිද? හරි නේද? ඊට පස්සේ අතින් අපේ non conservative process එකක් කරමු. Right, yeah. After that, right? When the work done by a force on a particle, when the work done by a force on a particle on a particle between two sorry, on a particle that moves on a particle that moves on a particle that moves through a closed path that moves through a closed path is not zero. It's not zero. The force is non-conservative force. The force is non-conservative force. Then write work done by a non-conservative force on a particle. Work done by a non-conservative force on a particle non-conservative force on a particle that moves between 2 points depends on the path depends on the path depends on the path the particle follows depends on the path the particle follows. Write these examples of non-conservative forces. Right. It's, frictional force, is example of non-conservative force. Of course, it's example for non-conservative force. Right. Okay. Then right. Right there some it's another thing we call this mechanical energy conservation, right? Mechanical energy conservation means that we consider only the mechanical energies. So in a mechanical system, if there is no any other form of energy is found, so then only the potential and kinetic energy we considered as they should be considered. The potential energy plus the kinetic energy of the system should be remains constant. So it cannot be changed because if there is no any conservative forces, non-conservative forces applied to it. If that's non-conservative, if the work done by the conservative force, that's only the system. You have only the forces applied on that system is conservative manner. Then you can say that the mechanical energy of that system should be conservative. Conservative forces විතරයි මනක් තියෙන්නේ. that's all the works are done in the system by the conservative forces. Only you can say that this total mechanical energy should be conserved. That means that the sum of the potential and kinetic energy of the system should be remain unchanged. History right there. Okay, then right there, it's mechanical energy conservation. Right there, that's mechanical energy. Mechanical energy conservation. Okay, then right under that, when write the forces acting on the system, when the forces acting on the system are conservative in nature, the mechanical energy of the system remains constant. Mechanical energy of the system remains constant. This is important, right? This means that's a kinetic energy plus the potential energy of the system. It is a constant. If all the work done done only by the conservative nature. If there is an unconservative forces acting on this system, you cannot write like so. Then the work energy principle you need to use. But the mechanical energy conservation you can apply if you can ensure that there are no non-conservative forces acting on the system. That's all the work done by the system is under conservative manner. You can write in this way. So according to this, you can write the change in that's a kinetic energy change after and before, and potential energy change after and before something happened on the system. The change in potential, that's if the change is a constant change, that is you can say then it's zero. This is the energy, sum of energy is a constant. This is the changing energy. That's if something happened to the system, before and after. So difference between them should be zero, because then if it is zero, you can say that's initial energy or equals to the final energy. So how can I write this kinetic energy change? So it's the kinetic energy of the final system minus kinetic energy of the initial potential energy final and potential energy initially actually equals to C. So this implies you that's a kinetic energy before and final kinetic energy and potential sum of the kinetic and potential energy final situation, and C equals to sum of the kinetic energy and potential energy initial. Right. So this two you can use. Let's see. Final total mechanical energy equals to the initial total mechanical. Initial total mechanical energy. Is the conservation of mechanical energy, right? This you need to be clear idea about this. This can be applied when the case of the work done on the system is under the conservative process. We'll discuss some examples then. Yeah, that's kinetic energy half mv square. This half. This is mgho half kx square. So we can say like that. You finish this writing, let me know then I write in the other form in the design. Finish writing. Still writing or finish writing. To finish, let me know. So okay. I go to the other side, right? Finish, let me know. So this gives you that in the kinetic energy case, you can write as half mv square and gravitational potential energy mgh, and in elastic potential energy you can write as half k square. The sum of this all is a constant. Constant at any event, any case, any time of the system during its change in the converting the energy. Okay, one by one we can change energy from one form to another and another form to another like that. So this thing finally need to keep in mind. So let's see about example. Example, right? Yeah. Find the okay, first you write the velocity at the point capital A, the velocity of the particle at the point, velocity of the particle at the point capital A is 5 meters per second. Is 5 meters per second. The mass of the particle is 10 kilograms. Find the velocities of the particle. Find the velocities of the particle at point B, C, and D. At the point B, C, and D. It's 10 kilogram. This point velocity is 5 meters per second. And also you need to consider that it is follow this path when it's moving, right? Projectile again is follow the path given by the red color. When it's moving through this path, you can find these velocities at this point. Velocity mean actually I'm asking about the speeds. Velocity means speed because direction consider download. And assume that the path is smooth, right? But, yeah, this path is smooth. Assume that the path is smooth. How you can do it? It is smooth, so there no friction. You need to ensure that because as this when the body is moving through this path, the forces acting on this body here. Let's say this force acting on this body, its weight downward and normal force is acting uh, perpendicular to this path. That's all. This normal force is perpendicular to the direction of its motion. So then it's not do any work. You know that the work done by the forces perpendicular to the direction of its motion, it's zero. We discussed that in the work. So here the work is done on this particle by the weight of the body, right? So weight of is a conservative force. So then you can apply the mechanical energy conservation for this, right? So we're using mechanical energy conservation. Here this example you can write like this. I will discuss this thing one by one. There's some examples for this mechanical energy conservation, right? So and some different applications I will discuss. In using mechanical energy conservation, you can write it's a total mechanical energy. This total mechanical energy is ME is the mechanical energy at A. So equals to the total mechanical energy at B. And also should equals to total mechanical at C and D also. So you can equate it like this. You can write find the velocities at these positions, right? So then total mechanical energy at A, they given writes potential energy, that's mgha plus half mva square. That should equals to the mgh at the B and plus half mv b square. And m is the m cancel all the places the same mass you have, so it should cancel out, right? So the g is 10 and h is 10 and half va the given as 5 meters per second, 5 meters per second, and g and h is at the b the height is 5 meter and plus half the b sky you can find it, and it's 100 and this is 25. So half of that is 12.5 minus this part will come to this side is 50 and half b square. So you can write in 112.5 minus 50, 60, 2.5, 125. So v square is 125. Square root of this in 5 root 5. Okay, so then the VB equals 5 root 5. Similarly, you can write the equation for this C and G also. Clear? I got the other side and right, then the other parts. So the mechanical energy at A, that should equal the mechanical energy at C also. So the half A square, that's mgha half mc square mg. And write the same cancel, so then you can multiply by 2. You can write this a square plus 2gha and c square plus 2gh. So we see the right there. That is equals to the a square. I'll write this 2g take out and ha minus hc. And this 5 square as 2g is 10. This is 10 minus h is 8. H is 8. So this is 2. And then it's getting negative value, no? So it's have no, it's positive. That's 2 and 40, 40 plus 65. Let me see, is the square root of 65. It's 8.06 meters per second. This, then the same thing you can do at A and C. Also, the mechanical energies are equal. Then at the D, you can write the same way. I'll write this equation directly now. This VA star, that's plus 2GHA and minus equals to VT star and plus 2GHG. This part is 0 because there's some considering the measuring the potential energy with respect to this level T. So you don't need to consider bar this, then VD that's equals to the square root of VA square plus 2GHA. And this is 25 plus 2G and A is 10 again. So then 125, 225. So square root of this is 15. Okay, that's the way you write. And what's happened during this motion? Let's see. So at here, when they come down, the potential energy decreases, the kinetic energy increases, right? So decrease the in potential energy, that's equals to the gain in kinetic energy. And when they come up to C, so what happened then again? Potential energy increase, then subkinetic energy decrease. So that's why here the velocity is much greater. There's pi root pi, something 11 point something, right? So in here it's 8. So it's kinetic energy reduced, that the velocity also reduced, but potential energy increase. And here that potential energy again it's converts to kinetic energy at this position. So this is some considering at the potential energy 0 level. So potential energy total become kinetic. The total energy of this at this point, that's equals to total energy kinetic energy of this point. So here both the kinetic and potential energies are there in these positions, but here there's only kinetic. That's why that's how that energy converts, not destroyed or not created during the motion. Or any point the energy will not be destroyed as non-mechanical energies. So in the case of mechanical system, the non-mechanical energies, we can consider this as energy loss to this system. There is unwanted energy. Yeah, you can do that. That's something. I write in this format to write it in separate way, but in the case of this, if you can calculate the total energy at this position, as you ask in this thing now, so you can write as a potential energy mgh, that is mass is 10, g is 10, and 10 is 1000 joule. And the kinetic energy you can write as half into 10 into 5 square. Okay, that's 250, and then total is 1250. This is the total energy, initial total energy. So then you can equal directly this value for this any points. It's okay. I think you asked that question. No? Right. And other thing is that we don't need to write the equation for this point and this point always. You can write the point from this C and D also. That's a mechanical energy at C and mechanical energy D is also equal. And mechanical energy B and mechanical energy, if someone asks that's what is the velocity at this position, the same thing you can write in. If they ask me to, let's say, if at the same height, the 5 meter, they ask in the what is the potential, what is the velocity at this point? It is actually similar to this point because the potential energies are equal. So then their kinetic energy should be equal to this level. So then you can write this in that way also. When you write, you can write the mechanical energy at B. That's also equal to mechanical energy at D. Or you can directly calculate this value at the first position, then substitute it for other positions also. So anyway, you can write. The way of we are writing it will be different for different cases, but in this format I use because to identify that what are the energies associated with those points and those bits, right? Because in the questions we need to do it for only one place. That's it. Here, then you write a smaller topic as the energy loss. It has a mechanical energy loss. Let explain about this also. Mechanical energy loss. Right, lost. Okay, then mechanical energy loss. Okay, then right there, the energy of a system, the energy of a system is converted into the energy of the system is converted into non-mechanical forms, non-mechanical forms or non-mechanical energies. Energy of system. If the energy of the system, right? If energy of the system is converts or transfer into non-mechanical forms, non-mechanical forms as such as heat, sound, such as heat and sound. Those energies are called mechanical energy loss. Those energies are called the mechanical energy loss. Mechanical energy loss. Then put a sign right there. Energy loss means energy loss means that energy converts to unwanted energy. Energy converts into unwanted energy, but not the energy destroyed. Not the energy destroyed. So mechanical loss you can write in initial total mechanical energy minus final total mechanical energy. It's not the final minus initial because its loss means final energy is less than the initial one. So then you need to subtract it from initial. It's initial energy to minus the final one, right? The final energy should be subtracted from the initial one. So I will write it as it is delta E or loss. I can write as initial kinetic energy plus initial potential energy minus final kinetic energy final potential. So this is equals to the maybe heat, sound. So can I write something because that's the work done due to the against the friction. That's stored as heat mostly. All right. Finish the writing. Let me know. In, okay. Then write some applications of mechanical energy conservation. Uh, application of mechanical energy conservation. That's only one application I will discuss today because I forgot about that. You have a class at 7, no? So then I will discuss this only first one, and next one we discuss next week. Then only one we discuss and then finish the class, right? Forgot about this. I had to do that all thing, but I just remember you mentioned me that you have a class at 7. Okay, then I write some applications of mechanical energy conservation. That's first one. I write as the motion of a particle along a smooth path or smooth track. Motion of particle along a smooth track. The similar thing that we discussed in the question. an example I give you. Say we have a smooth track like this. Okay. Smooth track you have like this, right? And also we think you can write there that's consider consider particle is released, the particle of mass m, consider particle of mass m released at rest, released from rest, released from rest at capital A, at the point capital A, at the point capital A along the smooth track as shown in the figure. Along the smooth track as shown in the figure. This is at this point is zero, no velocity. It's released from this point, right? Mass of this is m. And let's see the velocity of this point. That's v2. Let's see. Here v1. We consider it is 0. And here it is v3, and here it is v4. Let's see. Then it's okay, then you can draw this track and then write there forces acting on the particle during this motion. During this motion are, first one you can see here that I will consider this point is in this and somewhere here in some middle point, and this forces is normal force R is there, and weight is downward the same G. These are the only two forces acting because no friction. It is a smooth track, right? This is smooth track. Yes. And then the forces acting on it, that is the weight of the particle, weight of the particle, that is mg, it's vertically downward is acting on it. And second one, normal reaction, normal reaction, which is that's perpendicular to the track. That is R, that's perpendicular to the track, right? So this level is a reference level. You can consider as a potential energy 0 level, or we call it a reference level. And try it as potential energy 0. This thing you can write that forces acting on the particle during this motion are weight of the particle is vertically down, and the normal reaction is perpendicular to the track. Okay. Then write the normal reaction So R is always normal reaction, is always perpendicular to the direction of the motion of the particle. Direction of the motion of the particle. Motion of the particle. Therefore, no work done. No work done by it. No work done by it. And next point, right? This since the track is smooth, since the track is smooth, no friction, no friction there, right? Since the track is smooth, no friction, right? So then this work done only by the weight applied on each. So then right there. So that you can write therefore work done only by the gravitational force. Gravitational force, that is within bracket the weight. Since the weight is, or gravitational force is, it's a conservative force. A conservative force. Mechanical energy of particle at any point remains constant or remains unchanged. At any point is constant, right? Is constant. So that means you can apply the mechanical energy conservation, right? So that's the thing you need to do, because if you have to know that how we can apply this mechanical energy conservation. So that's why I'm writing this thing, get an understanding. So if you know that thing, you don't need to write anything. You can directly substitute it using the mechanical energy conservation. I like it. But if someone asks that how you can apply it, why, what is the reason for that? So then you can write. You need to give that. This statement you need to write. What are the forces acting on it, and what are the forces which contribute to do the work? So then that's if that forces are conservative manner, so you can apply the conservation of mechanical energy. So according to this, you can write this initial point, that's potential energy only, that is mg1 h1, and second point, that's half mv2 square and plus mg h2 there, and the point C, this third portion, that's half mv3 square plus mgh3, and finally that's at the reference level, so no potential energy there, so it's equals to half mv4 square. So this is the way you need to write. Any point you can write in this way. Okay. That's all. That's let's stop the class today. And in next week I'll discuss the other part. So we need to discuss about some applications related to this mechanical energy conservation. We will discuss some other applications like the object moving in gravity and object moving as a pendulum, that's a harmonic motion, and when the object is attached to the spring and then moving, so how that's mechanical energy is conserved. And then we'll discuss some applications of this all energy, work energy, and we need to be discuss about the power also. So we'll finish that part in next lecture. Okay, you have some questions or any doubts, points, you can ask me. If not, you can leave because you told me that you're having a class at 7. Okay, good night and God bless.